All right, let's get started. So last time we introduced multi-objective optimization and Pareto optimality. So Pareto optimality being a way to balance objectives to ensure that when you're doing a design problem or when you're trying to come up with solutions for stakeholders, the focus is not on finding a particular solution, but on excluding solutions that are clearly bad, and that there are better solutions that would be better in all of your objectives. And so it's for finding the solutions that are really on the trade-off space. And so if I was to summarize kind of like, to me, Pareto optimality is a very engineering way of thinking things, because as engineers, we really should be always seeking the Pareto frontier. If we have two objectives for anything, so if I were to draw, say, two objectives, F1 and F2, so this is just objective 1 and objective 2, then what we're saying is that there may exist a bunch of solutions that are down here, but of all of these solutions, there is something we can do that can make both objectives better. So if it's good, if this is the good direction, and this is the good direction, then there's something to do. We can always make things better. So if you're designing a classifier, for example, you often think about type 1 error and type 2 error, for example, false positive rate and false negative rate. If there's something you can do to that classifier that makes both error rates better, then you should do that. That would be a better classifier. Eventually, you will push up against a constraint where you engage some fundamental constraint of the universe that says that in order for me to have a better type 1 error rate, I got to have a worse type 2 error rate or whatever. Eventually, you're going to hit that point, and then you got to make some hard choices about, well, what error rate do I really care the most about? But you need to get to that point. That is your goal as an engineer, is to design systems that live on trade-off spaces. If you're far from the trade-off space, then there's a lot of work, easy work, that you should do. You can't hand someone a solution to say, things could have been better in every single way that you like, but I just chose not to make them better. Our job is always to find out, how can we make things better in all of these different ways? And then finally, when we hit that fundamental trade-off, that lower limit, the Kramer-Rao bound or whatever, you've hit, where you said, I can't do any better, then you can engage the stakeholder and say, all right, there is a speed accuracy trade-off right here. There is a type 1 error, type 2 trade-off right here. Precision specificity trade-off. There are, I've engaged this trade-off. I can do it a bunch of different ways. You have to tell me what you care most about. If you don't know right now, then I'm going to give you a community of solutions. And then later on, when you do know, you can choose which solution you want and then go with that. And all I'm going to do is hand off this vocabulary, hand off this population to you. So that's really what we're seeking out, is this special set of solutions that'll live in this area. So there's this sort of boundary here, and we can think of these solutions as points along this boundary. And so these are some of our bad solutions. So we've got bad solutions, and then we've got the Pareto frontier. Of solutions in trade-off. And it's always good. So it's always good to move in this direction, but the frontier is the limit on how far you can move in that direction. Yeah.
I remember last class you said how each point along the frontier is different sigma value, and the F1 minus sigma F2 is maximized.
Right.
So And you were talking about using the evolutionary algorithm to get there. But what if I were to just like change sigma incrementally from like 0 to 1 and just maximize it each time and get that frontier that way?
Yeah, in well-behaved optimization objectives, so basically, if you imagine if I had a bunch of optimization objectives that were convex, for example, then I can get the entire frontier by solving a single optimization problem, exactly as you say, where I'm going to solve, I can think of this Pareto frontier as solutions. For example, this is if I'm saying maximize WF1 plus 1 minus WF2, where W is any value between 0 and 1, then I could solve this maximization problem over and over and over again for different W values. And that would allow me to get along this frontier. So that would be one way to get this frontier under certain assumptions about the well-behavedness of these two functions here. So things get a little hairier when these functions get pretty ugly, and if they sort of have a lot of interesting, like if they've non-convexity, if they've got gaps, there's a bunch of other little things that this may not end up actually finding the whole frontier, but this generally for almost every realistic optimization objective, then you can think of every point along this frontier as one particular W value. So this might be, W is close to 0, and this down here is where W is close to 1.
I've heard that term used before, convex and non-convex. I'm not sure I understand what that's.
Oh yes, so the term, so when I refer to convexity of a function, so is I'm just referring to its curvature. And so if I'm talking about and so this is a little bit of a tangent, and that's not meant to be a pun, but if I have a function f1 of x, then convexity is basically means that, so if I were to graph this function, if I were to pick any 2 points on the function and draw a line in between them, every point on that line would be above the function. That's what convexity means. And so, and concavity is sort of the opposite of that, where so if I were to flip this around, then a concave function would say that every point would be below the line. So that's all sort of convexity is saying, is that it has kind of a consistent curvature, so that that if you, to put it in sort of a simpler terms, if you were to find a point where f prime is equal to 0, then if it's convex, then that's a minimum. Okay. Well, if I know that's, yeah, so great. So this would be like f prime is equal to 0 and f double prime is less than 0. That sort of captures that. Okay, so so this is just our general, this is this Pareto framework. So we are looking for this community of solutions. So I'll write that community of solutions. So it's a set output, and we might refer to particular spots, in this community, or different values of W. We can think of them as niches, where we're not saying one niche is better than the other. We're just saying in some niche, there's a bigger prioritization for speed, and another niche is a bigger prioritization for accuracy. You think about, in terms of marketing, you can say, so you hear this, universities will talk about this as well. They'll say, we can't beat Stanford at its own game, so we can't offer the things that Stanford wants to offer. We can't be Stanford. We're not ever going to beat Stanford. So we need to figure out something that we can do that's different than Stanford that only we can do. So what they're basically saying there is Stanford has optimized one thing, and we are not ever going to be able to catch up with them on that one thing. And so if we just try to mimic them, we're not going to win. That's the same thing as an animal saying, there's already an animal in this niche that is dominating this niche, and they're always going to find all the food before I find it. So we can't just try to be a copy of that animal. We have to do something different. And so that's saying we are going to focus on this other optimization objective that Stanford doesn't focus on. And if we go in that direction, then we will attract, enough, we don't have to compete with Stanford, we can coexist. So there are coexisting solutions within this community. And the reason that they coexist is because there are multiple ways to achieve fitness. There's multiple ways to get market share. There's multiple ways to get reproductives into the next generation. You don't have to compete with the top dog. You can be a cat, as a sort of example there. So that's what I mean by niches. These are sort of different weightings of optimization objectives. And so we believe that natural selection pushes things toward the Pareto frontier of all of the different characters within phenotypes. And so, instead of referring to optimization objectives in a natural sort of in an evolutionary sense, we might refer to this as a character. So character 1, and this over here as a character 2. And all of the characters together make up the phenotype, and all the phenotypes are judged by their fitness. But there's multiple ways for you to have 10 offspring. You can have 10 offspring being the fastest predator. You can have 10 offspring being the most cryptic prey. So if you can hide really well, then you can coexist with the predator who can run really fast. You can both live in the same area because the predator is going to be eating different prey and you're going to be hiding from the predator. You're both going to be fine. You're both going to be coexisting. You're both going to be having 10 offspring. So you'll both have the same fitness. So you'll both be sitting on the same Pareto frontier, but you'll have been designed, if we want to use that term, based on very different optimization pressures. And so that's what we're trying to now build, our optimization algorithms that, like nature, produce diversity of solutions simultaneously, not by solving this problem over and over again. Okay, questions about that? Is that clear? Let me see if there's questions online. All right, just confirmation about hearing. Okay. Great. All right, so we started to introduce some of these algorithms last time, and I guess not surprisingly, maybe, when people started thinking about multi-objective optimization algorithms, and of which them evolutionary algorithms are extremely common ways to solve multi-objective optimization, just because evolutionary algorithms have this multiple, using multiple solutions simultaneously, because you want a set-based output, you want a community output, and you automatically get that for free in an evolutionary algorithm. So a bunch of other optimization algorithms don't have communities of individuals running around, so they often do not naturally solve the multi-objective problem, but evolutionary algorithms do. Some of the other swarm-based algorithms we'll talk about in a couple of units also have natural adaptations to the multi-objective problem. But evolutionary algorithms, I'd say, were some of the first to really get at this multi-objective problem. Okay, so I kind of mentioned it's natural for us to think about the weights as a way to conceptualize what's going on here. And so it's natural to believe that the first evolutionary algorithms to produce multi-objective outputs just kind of toyed with this idea of how do I kind of create diversity in the weights in the population. And if I could somehow have a diversity in the weights in the population, then maybe my population will tend to move toward the frontier. But then when it hits the frontier, it'll maintain diversity along it, which is the ultimate goal. And so I mentioned last time that some of the first approaches were just these random, well, I don't know if I want to jump straight to some of the first approaches were these weight-based, like for example, our example one is the weight-based genetic algorithm for multiple objectives. And this fits within the category of weighted sum approaches. And as I started to talk about last time, in the weight-based GA, it's just a traditional GA. But you're going to make the weights part of the chromosome. So every individual's genotype will have potentially a different set of weights. So this is kind of an interesting thing, is that you create a diversity of individuals initially in your GA, and every individual is sort of gauged by a different measuring stick. So they all have the same fitness objectives, but they combine them in different ways. And so one individual will receive a fitness score based on a combination that might prioritize objective 6, and another individual might be a mix of objectives 2 and 3 primarily. Another individual is pretty much all objective 1, and they run around like that. Now, the weights themselves can be subject to mutation and crossover. So what that can mean is you can have strategies evolving that are really well suited for objective 6, because for a long time they've been evolving along with objective 6, and then suddenly, due to crossover, those same strategies are being tried out with objective 3, because they've just crossed over and then basically just swapped out their weights for the weights for someone else. So now we get to see how that strategy works for objective 3, and it may not work very well at all, but maybe with a slight mutation it works pretty well there. So you get hopefully a promotion of diversity, where you get things that are kind of, the whole mixture of these different things here. So just to write that out, we use weight vector I'll say W1, W2, up to Wn as part of chromosome. And there was a question last time, is there a constraint that the weight vector adds up to 1? And I forgot to take a look at WBGA-MO to see if they did that. I think off the top of my head that they did make the constraint that the weights have to sum to 1. It makes sense that they would, but I think it would work just as well if they didn't. It just might take longer. But so we'll just say, without me verifying here, that these weights for each individual, before you allow the individual to go to the next generation, get normalized equaling to 1. This is conjecture. And then so then we calculate each individual's fitness using their own weights. And then that way we hopefully optimize multiple trade-offs simultaneously. All right, so that's a relatively simple approach of shoehorning the multiple objectives into a traditional GA. We're going to update the fitness function so that it combines multiple objectives, and we're going to combine it differently for every individual. And we're going to allow those combinations to mutate themselves, because as we mutate the combinations, we start exploiting different areas of that community. So you could start out with a random community that's somewhere down here, and they'll gradually be drawn up to the frontier, and then as their weights mutate, then they'll be drawn to different regions of the frontier. But because their weights are mutating, then hopefully they don't just end up all being attracted to 1 point or 2 points on the frontier. That's the hope. So any questions about this general approach? Pretty straightforward. As with most straightforward approaches, works marginally well. This is a good example of a proof of concept, but most multi-objective genetic algorithms nowadays don't use approaches like these because it doesn't really give you the diversity that you want. but it was one of the first kind of approaches because it's pretty easy to implement. Okay, so so then you can imagine variations on this theme. So the other kind of popular variation was the random weight GA. Or RWGA. And so the basic outline of this algorithm is it's a slight modification of the GA itself, but only slightly, and you can kind of maybe guess how it's going to change here. So we have a random initial population. Then we assign fitness by, we're going to draw a random weight, which I'll call U of K, from 0 to 1, for each objective. And so we draw a random UK, and then I turn that into a weight by normalization. So then normalize. And so I normalize that by just creating a WK is equal to UK divided by the sum of all the U's. So I'll call it UI. And then I calculate fitness based on random weights. And that ensures a convex combination. So then the rest is similar to a normal GA. So typically we're going to do proportional selection in the original RWGA at least. We all know what that means now. We do mutation and crossover. And then they have elites in this one. We didn't do elites in the GA that we wrote, but I talked about them a little bit. But they have a set of elites, so they update E, it's a set of elites, with newly discovered, and I'll introduce a term that I haven't formally defined yet, but I'll do that, non-dominated solutions. And then we randomly remove some number, so I'll say NE solutions from population and replace with members from E. And then finally, check our stopping condition and iterate if necessary. All right, so there were two major differences. The simple one, we randomly assign fitness. And then the other thing is that they are constantly updating this set of elites, but these elites are non-dominated solutions. Now, what we mean by non-dominated is these are strategies for which there is no other strategy in the population that does better than that strategy in all other optimization objectives. So when we talk about Pareto optimality, we will sometimes use the term a dominated solution. A dominated solution is one that again, that is a Pareto movement from the solution that it is dominating. And so a dominated, or I don't know if I said that backwards, a dominated solution is one where there is a solution that dominates it that is a Pareto movement away from it. So if there is another solution that is better in all optimization criteria and all optimization objectives than this solution, then that other solution we say dominates this solution down here. So when we're running these multi-objective optimization algorithms, we're trying to create a set of non-dominated solutions that are always non-dominated, that are the non-dominated solutions, because the Pareto set, the Pareto community here, this community is a community of so-called non-dominated solutions. So again, Pareto optimality is really about excluding the bad solutions, not finding the best solution. And so the solution along the community are all the ones that can't be excluded. And we also refer to those as non-dominated solutions. So these, it's referring to the non-dominated solutions in one generation of this. We're hoping that this will converge so that the non-dominated solutions in each generation will end up converging to a sample of the Pareto frontier. All right, and so the interesting thing about this, especially this random removal part, is that it has two populations that it's maintaining. It has a memory of the non-dominated solutions that it's constantly updating. And by, notice I say update here, this means that if you find that one of your elites is now dominated, you get rid of it, because you've now found something that dominates it. So you look at all your elites, and then you see if all the new strategies you found, is one of the new strategies, does it dominate one of the elites in your current elites? If it does, get rid of that old elite, replace it with a new one that dominated, and so keep updating that. So we're constantly updating our set of what we think are samples of the Pareto frontier. And whenever we have evidence that it's not on the Pareto frontier, we exclude them from that set. So that's what we're doing right here. And then we leave some random individuals in the population, but then we also just get rid of some of them and then put some of our elites in instead, just to keep things interesting and kind of drive a little bit more pressure. And we just can't let this thing run. And so we're constantly having the population of competitors and the memory of all of our dominators in here. And like I say, they're dominators, meaning they're non-dominated themselves. So it is a variation. It is still in the spirit of the weight-based GA, but it is actually a significant variation on how the GA runs. So questions on this, on the random weight GA? Yeah.
So are we generating a random weight vector that we use for all of the individual population, or are we doing it for
The random weight vector, and this is another, so you also were the one who asked about the previous question. I often, it's so been, and again, RWGA is so deprecated, I'd have to look back to confirm whether RWGA does it every time. My gut feeling is that RWGA does this every generation, and then everyone in that generation is assessed by this weight. But I hesitate, because that would mean that every generation is going to pull the generations to one spot on the frontier, which is why if I was writing to RWGA, I probably would be tempted to have this, every individual would draw a new set of random weights to make it very similar to weight-based. So I don't know for sure, but right now I guess I'm leaning towards mimicking the weight-based, where every individual gets a new randomized combination. Okay. See, there's questions. I see some questions online, and let me say that E will be final solution set at termination. Okay, so I see are elites subject to random weights from the subsequent step is one of the questions there. And the elites, again, are just a memory. So when they're put back in the population and that population cycles, then they will be subject to whatever weights assess their fitness in the next step. So the elites don't get a pass on competition. The elites are just kept over as memory of what's been found so far. And so the idea here is in theory, you might find some elites up here, but then the algorithm is going to shift its focus down here. And so you want to remember that these were still up here, which is why we maintain two populations, a memory of the non-dominated ones, and then also the freedom to walk around the Pareto frontier. That's what they're trying to establish. So anybody who makes it into the population will be scrutinized by these weights and then seen if they end up getting to be challenge the existing elites by adding a non-dominated solution and removing an old elite. So yeah, elites don't get a free pass. They definitely get to be evaluated later. Oh, great question. How do we know it's a non-dominated solution? So how do you figure out if it's a non-dominated solution? This is an interesting computational problem. Every time you have a strategy, you got to do all the pairwise combinations to figure out if another strategy, if I have two strategies next to each other, I need to say, does this strategy dominate this strategy? Well, what I need to do for that is for those two strategies, I need to go through every optimization objective. So you have n optimization objectives and ask for optimization objective 1, who's better? For optimization objective 2, who's better? So for every optimization objective, I've got to evaluate the objective twice, or I have to know, maybe stored in memory, I've got to know how well each strategy does on all of those optimization objectives. And then I compare each one of them. And if I find out that after that comparison, that this one individual did better in all of the optimization objectives than the other one individual, then I clear out the one that was worse because it's now been dominated. It's out of consideration. We do not care about it anymore. We only keep the one that's non-dominated. Now, if I find that sometimes one solution's better and sometimes the other solution's better, then I don't have evidence that either one of them is dominated. And so I keep them up for consideration as non-dominated. So every pair of solutions has to be evaluated against every optimization objective to figure out if there's a domination condition there. So solving these Pareto optimization problems can involve a lot of computational complexity in that you have to do a lot of pairwise comparisons of a lot of things. So I hope that makes sense, that it's definitely much harder than just calculating fitness once. There's a similar question. And then there's a question, if the elites are subject to random weights, do they lose their elitism? Yes, so that again goes back to the previous question, is that if an elite gets placed into the population and then the population ends up here generating some variations that then when they get back to the elites, they compare to all the elites. And now one of the new variations ends up, possibly an offspring of the previous elite, ends up dominating one of the old elites, then the old elites get wiped out. So this group of elites doesn't necessarily grow. You can actually start with a huge number of elites, and then one solution might dominate all of them. And then all of the old elites get thrown away. And the new elite set is just that one solution that dominates all of them. Okay. And these are all great questions because as we get to more complex multi-objective population algorithms here, then these ideas will become more and more salient and at the sort of the front of the algorithm, where we culminate in so-called Pareto-ranking, which is all about this. And then there's this question, essentially, are you cantering the f of x? I don't think I understand the question there, so if I don't have an answer to that, then maybe we can take that offline. Okay, so that's RWGA. Everybody okay with that? Okay. And there are sort of interesting analogies where you can think about these two populations together as kind of one of them's off on an island and so they're sort of separated, and then occasionally there's gene flow between the islands. I'm not going to go into that too much now, but if that helps you, if you want to kind of think about that, you can think about that. And as we get into multimodal optimization, then that idea of islanding and gene flow will become really important. So we'll get there. Okay, so those are our kind of weight-based GAs. The other case, there's three cases I kind of want to go over here. So the other case we can consider is, instead of playing with the weights, we can do an alternating of the objective functions. And so another batch of multi-objective genetic algorithms were based on this idea of, instead of creating a single fitness function, we are going to take a population and sometimes put individuals through challenges based on one objective, and then other times put them through challenges based on another objective, and so on and so forth. And so we're going to challenge them on one objective of a time, but which objective they get is effectively random. And so that hopefully will create a diverse community of solutions where some will be good at one objective and some will be good at another objective. Some might be a mixture of the two, and so on. And so the one that I want to focus on is VEGA. And yeah, all right. So the main example of this, so I'll call this example 3, is the vector innate evaluated GA, otherwise known as VEGA. And this one is going to maintain sort of K subpopulations that are each evaluating a different objective function and migrating between populations. All right, so the idea here is I'm going to run a conventional GA in a bunch of little subpopulations. And then in between runs of my conventional GA, I'm going to swap some population members from each subpopulation. So the idea here is, if I've got, imagine I've got n individuals, so n total population, and I've got K objectives, then I've got a subpopulation size of, I think I call this NS, for subpopulation of n divided by K. And so, so now the way VEGA works, the way VEGA is implemented, and of course you could implement this different ways, is you have a random initial population. Then we do, we check our stopping criteria. So of course, initially, this is passed on. So that'll be where we repeat. Then we randomly sort the population. So this is where VEGA gets its name. And this here is meant to model migration. So you'll see what I mean by this, but But basically, we're going to store the whole population in a vector enabled. And different, and then like the first NS regions of the vector will be for objective 1. The second NS will be for objective 2, and so on and so forth. So by permuting the vector, we're creating migration among island objectives. Yeah.
In this vector, you're storing values of X, like,
you can think of it as storing the strategies themselves. So I guess that you could say that as like the values of X. Sure. And then so for each objective, which I think I call K. So from K, from 1 to big K. So this is little k and this is big K. So I guess I'll make this big K to try to make that a little clearer in my awful handwriting. Then I assign fitness to the kth population based on objective K. And then I select NS solutions from subpopulation, from the subpopulation, combine the subpopulations, apply process or iteration. So the, let me write this out. So I'm going to assign fitness to the kth subpopulation. And so you can again think of there being all of these subpopulations of size NS. And you can think of this as objective 1, this is objective 2, this is objective 3, and this whole thing here are our N individuals. So I assign fitness to the kth subpopulation based on that objective K. And then I select NS solutions from that subpopulation. So, so however you're doing your fitness, your selection operator, you can think of the assigning the fitness as creating growth within the population, but then that population has to fit within our NS bubble. So this really together is just a selection operator that sets up the next generation for the next GA for kind of that subpopulation. And then if I seem distracted, it's because like in my ear, like I hear music. Like I think it's coming out of the AirPod. It's not like coming out of my head. And I don't think it's music from like somebody with their mic on, although it could be. It almost, oh, you can hear it from here? Oh, that's interesting. Oh yeah, I wonder, let me see if there's, under the participant list here, if somebody's gonna get muted. All right, everybody online can still hear me, I assume, right now? Yeah, I see the caption, so good. All right, well then we'll just cope. I'm glad it's not just me who can hear it, so thanks for confirming. Let me get rid of this chat bubble. All right, sorry about that, folks. Okay, so So yeah, we select those solutions from the subpopulation. We combine those subpopulations back into our A population of size n, and then we apply mutation and crossover. So, so combine subpops back into pop, or also I'll call it in pop, and then do crossover and mutation. And then we iterate. So this is step 2. And this is often referred to in VEGA as shuffling, or the shuffle. So it is, you shuffle this population, and based on wherever they land, that's the fitness that they have to deal with. And then they end up getting offspring based on that. And then that sets up the new population based on wherever the parents landed and how they were evaluated. And then those offspring, well, so then it's just kind of the standard crossover mutation dynamics. And so however well the parents did, that determines how they did within the subpopulation. And then from there, they could cross over, but they're going to be crossing over across the whole population. So the idea here is that I could still, even though they competed just within one subpopulation, like this one here, they could potentially still have sex across subpopulations, mixing components that are far off. So you're shuffling to determine how the fitness is associated, but then you're still mixing across a larger subpopulation. And so you can think of this, like I said initially, as kind of a GA applied to K objectives, like K different parallel GAs. But it's more nuanced than that, because you're just sort of assigning the fitness in the little sub areas, but you're still doing crossover across the whole population. So it was just an attempt for them to try to do better at it was just an attempt to try to create what they viewed was sort of speciation. So the thought was here is that possibly you could create, you'd have more pressure to create speciation into these niches, and that would produce more diversity. But it's totally empirical, and it turns out that VEGA is, I think you can show that VEGA cannot really do any better than the randomly weighted ones. It just ends up actually producing the same types of populations as the randomly weighted ones. And so neither randomly weighting or alternating objective functions, they all actually degenerate into the same type. And neither of them do that well compared to our last case, which is the modern way to do it, which is the Pareto-ranking approaches. So that's what I'm about to then cover here in the last bit of class. So any questions on VEGA? It's an approach not based on weight, but ends up producing the same outcome as the weight-based approaches. Let me see. I see, so for each chunk of the population, NS gets a different fitness function. That's right, but who is in these positions is going to vary. So because of the shuffling, then you might be up against objective 1 in the first generation, but then you might get shuffled into objective 3 for the next generation, and so on and so forth. And so where you are in the whole population determines how you're going to be evaluated, but then you may not stay there. So there's a lot of migration. Okay. All right, any other questions online? Still that? I'm pretty sure that projector is just dying. So maybe after class, I'll try turning it off and seeing if that fixes it. Okay, so neither one of these are particularly good relative to this last class, which is the modern way to do multi-objective genetic algorithms. And there are, of course, variations on this class, but they all kind of, the main features come from this. And so this class 3 is the Pareto ranking approaches. And it's one of these things where after you hear it, you wonder why somebody didn't come up with it first. But that's the way a lot of these things are. It's just a nice, simple, clever idea. It just takes forever to come up with the idea, but the once it's there, it feels like, you know, anybody could have come up with it. And the idea here is that we're going to assign fitness to individuals basically by how many individuals in the population they dominate. So if we have a population of 100 individuals, then if I dominate all of you, so I am better in all of the optimization objectives, I'm going to get the highest fitness. And if one of you dominates all but me, you'll get the second highest fitness, and so on. So it's like a ranking-based selection, but the ranks that we'll use for the rank-based selection won't be based on evaluating a particular fitness function. It'll be based on how many of the current population you currently dominate. That's the Pareto ranking approach. So, so that's all I'm sort of saying here. So I'm going to say rank individuals in population by how many others well, I'll say dominate them. And this is sort of the, if we're doing a minimization. So, so if I went minimizing, optimization objectives, if all my optimization objectives are better to be small, then this ranking will end up, if you're rank 1, if you're rank 0, then that means nobody else dominates you and you're kind of best. If you're rank 1, then that means that only one other dominates you, so you're pretty good, and so on and so forth. So whether we've got the ranking in one direction or the other, it's the same basic idea, is we're counting how many individuals are being dominated, and we're using that as our surrogate for fitness instead of the the optimization objectives themselves. So, so notice here that the non-dominated individuals all have same rank. And that's the beautiful part about this, is that this puts pressure toward the frontier, but when you're on the frontier, everybody's equal. So that allows for any initial diversity to be retained. It allows for new diversity, if you have diversity creating mechanisms, to be created, and so that you can actually create diversity along the frontier. All of these other approaches that were strictly tied to the optimization objective tried to, blend things a bit, but ultimately there was always a way that at a small scale, within a generation, that even those that were even 2 individuals that are on the frontier might, if you were using optimization objective 1 instead of 3, or using one particular weights instead of another set of weights, then those on the frontier could, at least at a small scale, one could appear to be better than the other. In this case, if you are on the frontier or getting close to the frontier, as close as anyone else has gotten to the frontier, you're no different than anyone else. And that helps preserve diversity as you're moving toward the frontier, because you're not getting rid of diversity in the small scale. So we define fitness by rank. And so the idea here is we can maybe sort population by rank. And then we can assign fitness by interpolation. I'm trying to decide how much detail I want to get into this. yeah, I'm just going to say assign fitness based on rank, and then we might adjust to penalize things that decrease diversity. So to penalize clustering, etc. And there are a number of methods for these, and we'll talk about these methods more as we start talking about multimodal optimization. So things like niche count, things like some like reducing fitness of those who have many others near them. And we'll learn other sorts of methods that are similar to this. And these all fit within what is referred to as fitness sharing methods. And so the basic idea here is that we're going to put pressure towards moving toward the Pareto frontier. As we do that, we are going to additionally penalize any sort of clumping that happens to occur during that. So we've got a general force moving things toward the frontier, either going down to the frontier in a minimization, or maybe up to the frontier in a maximization. So as we're moving towards the frontier, if things start getting close together, we reduce those fitness so that we don't necessarily completely get rid of them, or we might actually completely get rid of them and then create a new one randomly somewhere else. And the hope is that both of these things, reducing, are going to maintain or enhance diversity as the whole group moves towards the frontier. And that's kind of the goal here with all of these Pareto ranking approaches. Right. Okay, so and so that's trying to decide if I want to go. So as I go this, so especially over my pacing changes every semester because like the modality changes every semester that I've taught this. So I'm just deciding how much detail I want to go into, and that, or how much do I want to get into the next unit. And I think the next unit is going to pick up where I wanted to pick up off. So there's a number of different example algorithms like this. The most popular, so this MOGA was this kind of the most popular Pareto ranking algorithm that uses this type of approach. And there's the more modern ones though are NSGA and NSGA-2, and now there's actually an NSGA-3. So if you were to be doing a major research project with really sophisticated multi-objective that you were trying to do, so like if you go into a program like MATLAB, they're probably just going to implement MOGA. But if you're implementing it yourself or you're trying to do something more sophisticated, NSGA-2 is super popular for doing this, and now there's a new NSGA-3, and all of these approaches use Pareto ranking. But the way they differ is in how they maintain diversity. And they sort of clever ways that they try to either introduce diversity or not get rid of diversity as they're going. But they all basically work the same way, where fitness is a rank, is a Pareto rank, and you're constantly just trying to get rid of dominated solutions as they are outperformed by the non-dominated solutions. Okay. So questions on this basic approach, where it's just basically rank-based selection, like we've already learned about, but instead of ranking things by a fitness objective, we're ranking them by how many are either dominated by them or how many that they dominate. Pareto ranking. Let me see if there's questions online. So all the non-dominant ones of the same rate could have different phenotypic diversity, but the same rank, making them all Pareto with respect to each other. That's the basic idea is that all the non-dominant ones will have the same rank. So there will be no selective reason for them to be gotten rid of. Of course, they could drift away because drift is going to naturally cause is going to be a diversity reducing mechanism, but selection won't cause them to go away because they'll all apparently have the same fitness. Okay. And if you were to like drop into so I've got an example here. So like in MATLAB, you can make use of or take a look at the GA multi-ob function, and it uses MOGA. Which is an implementation of MOGA, which is Pareto ranking. And basically the way it works is it initializes the pop. It evaluates all optimization objectives for everyone in the pop. It assigns rank based on these evaluations, so based on Pareto dominance. It then does what's called a niche count. And so this basically is for every individual, how many neighbors are in each niche. So as we'll talk about in a little more detail when we talk about multimodal optimization, there are different ways to define a niche. Is it a niche in fitness space? Is it a niche in strategy space? Are we going to recalculate the niches centered on every individual, or are the niches going to be centered in the space? And that way, anybody who lands in that little niche bottle that we put on the whole space gets the same count. But they all basically are the same way, where it gives me sort of a penalty that I can give to every individual. So roughly speaking, this is going to be a penalty for clustering. So then for that penalty for clustering, then I can assign a shared fitness, which is basically going to be the fitness divided by the count. So if I'm the only one in my niche, I get all the fitness. If there's two of us in the niche, then we share the fitness. We both get half of the fitness from there. And that means it's half as likely for either one of us to get into the next generation, but it's just as likely for one of us to get into the next generation. So we are very similar solutions, and that's why we don't want to sort of overpopulate, because that's just going to get rid of the diversity. So that's an attempt to say, you guys are so similar, you're both fine. I don't care who goes through, just one of you goes through. And that's what niche sharing does, that's shared fitness. And then from there, we can do pretty much the, iterate with conventional GA based on rank, I'll say Pareto rank based fitness with fitness sharing by niche count. And if you run GA multi-objective, then you're going to get a population that if you then plotted against the different optimization objectives, you should, if it did a good job, see a trade-off, a frontier where, so a lot of times you'll get, like if you had F1 and F2, you'll end up getting an output where you'll get a bunch of solutions very close on a kind of a line, and then a couple of stragglers kind of hanging off the line. And I think GA multi-objective by default minimizes, and so you can imagine actually putting the stragglers being above the line. And then the thick part would actually be, this is our desired solution set here. But there's always variance due to mutation. All right, and that is basically multi-objective. So that's kind of our summary here. Is we've got two different weight-based approaches that are pretty much similar. We have Pareto ranking, which is really the right way to go. It's just been demonstrated time and time again. You get much, much better MOGAs, multi-objective genetic algorithms, if you use Pareto ranking as your fitness. But you then need to somehow maintain diversity, because still GA was kind of fundamentally built to find one solution. And so fitness sharing approaches, but what's nice about Pareto ranking is it doesn't sort of create an extra pressure for everything to come to one point, but it doesn't increase diversity. And if there's a lack of diversity just by random chance, it doesn't really do much about that. And so fitness sharing methods end up counting up how many individuals are in those niches and spread them out if there's too many individuals in one niche. It's kind of a mechanism for competitive exclusion. And then that hopefully gives you motion toward the frontier and along the frontier. All right, now a bunch of extensions. How do you deal with infeasible solutions? That ends up being, gets more interesting when there's multiple objectives, but those are, I don't want to spend a lot of time talking about that because there's a bunch of different methods that I can't say one is necessarily better than another, and it's very similar to the infeasible discussion back with the standard single objective GA. All right, so I think that's all I've got for you for this unit. I'm just sort of surprised that I didn't leave things out because I was running so far behind, and now we're back on schedule. I don't know how that happened. I'm just deathly afraid I forgot something. So, but somehow we just caught up. So are there any other questions? Let me see online if there's questions. I think the chat window changed. So the question online was, how do you find out the size of each niche? We're going to talk about details of that because this is going to come back for multimodal optimization. But there are several methods to do niche counting. And again, you'll see them again. I'll show you a couple of different options for multimodal because it's really important for multimodal. But just as a preview of that, it's kind of like I was mentioning before, you could imagine, for example, you go to every individual and then you say, I'm going to say in decision space, I'm going to set a Euclidean distance of 1 unit. So if I'm sitting in a decision variable, I've got X1 here, X2 here, and I'm going to draw a circle around every individual of 1 unit in every direction. And I'm going to call that a niche. And then I'm going to count how many other individuals are in that circle of 1 unit around that. So one way you could do niche counting here is I've got my X1, my X2, I've got some potential strategy here. It's got its own fitness, F. I draw a circle around it. Other individuals might be in that circle and other are outside it. So here I might say this has a niche count of 5 because there's 5 individuals inside that circle. So the actual fitness here is going to be F divided by 5 to account for the 5 individuals within that niche. So I can do that in decision space. So this is like niche counting. Or I could have done that, the exact same thing, but in optimization space. So I could say I've got the same individual, it's got individuals around it, I draw a circle, and then I can say how many individuals cluster around it. There's a bunch of other things I can do too. These bubbles don't have to be centered on individuals. They could actually be in the space itself. And so then I could say a priori that either one of these spaces, be it X or F, is cut up into blocks that I'm predefining as niches. And then I can say how many individuals show up. If you are in a block and that block has got 8 individuals, then the niche count for everybody in that block is 8. So I hope you can see that niche counting adds a significant other layer of computational complexity to calculate these counts for every single individual. And there are a bunch of clever ways to try to reduce that complexity. You have to consider what's the most functional. Most people find that counting in the function space is more functional than the decision space. But it might be easier for you to build a map a priori in the decision space where you don't have to do the count for every individual. You can actually do the count based on the location they're in. It might be harder to do that with a function space, and so on and so forth. So there's a bunch of computational issues in how to choose a niche count mechanism, but they all function very similarly where they penalize clustering. So we'll talk about other ways to penalize clustering. You might be able to dream some up. You might have seen some in machine learning and some of your clustering algorithms, maybe that promote clustering, and we just kind of do the opposite of that. But that's basically the idea of niche counting, is just tools for penalizing clustering. But I've run over, so if you need to go, feel free to go. If you have any other questions, I'm happy to take. Yeah.
Is it ever worthwhile to use a proper clustering algorithm here, or is it better to stick to the interval? Because the normal clustering algorithm looks over.
Well, we'll talk. That's a great question of are off-the-shelf clustering algorithms that you could use. We'll talk about that in multimodal, where we'll actually sort of see relationships between k-means clustering and niche counting and so on and so forth. So that definitely will come out. If there's any questions in class, happy to take them. Online, any other lingering questions? If not, you guys can feel free to head out, and we will see you next week, and have a good weekend. Don't forget about the muddiest point.